without further ado, I'd like to introduce our first guest. It's Mr. William Selby, and I've had the honor of knowing Bill for quite a few years. He's one of Sustainable Works' strongest supporters. Whenever Sustainable Works would have an event, Bill was the first one to sign up. Whenever Sustainable Works had a fundraiser, Bill was the first one to pull out his checkbook or his credit card. And I really must say, Bill Selby is one of the nicest people that I know. He has been teaching climate, weather, and environmental studies in the Earth Science Department at Santa Monica College since the 1980s. And the majority of his work focuses on in-the-field studies. I hear he takes his students on amazing field trips. I hope to one day join you on one of those trips. This year, Bill unveiled a major update and third edition of his book, Rediscovering the Golden State, California Geography. Bill has also served as a leader for the Center for Environmental and Urban Studies at Santa Monica College. He's on the advisory board of Sustainable Works, and he is also on the board of the Santa Monica Task Force for the Environment. I give you Mr. William Selby.
Wow, this is amazing. You know, I'm a little overwhelmed because when I look out in this audience, I see people that for many years I've admired, people I've looked up to in this community. These are the people who have made this community the great place that it is, and that's what makes me overwhelmed. I'm a little bit more nervous than I thought I would be, Gina. So if I make a lot of mistakes, I hope you understand. I do want to say, though, that Gina and the Sustainable Works folks, I've always said I was one of your biggest fans, and the reason for that is I think you've done more to make Santa Monica and the West Side sustainable than any organization, group, event that I know of. It's really remarkable what Sustainable Works has done.
And I have to counter that Sustainable Works wouldn't exist if it wasn't for people like Bill Selby.
Oh, I heard a voice. I didn't know it was yours. Yes, thank you. Wow, I thought this is really a church and we're being, whoa. Hey, I went ahead already. What? I guess I'm already nervous. Okay, there we go. So you want to, is my time up yet, Valerie? No? Okay. What I'm trying to show you here is the ozone hole. Most of you, oh, you know what? I was going to introduce all of this. And so what I'd like to do is have people leave their politics at the door just for a few minutes, because we're going to talk about scientific data. We're going to talk about objective scientific data. We're going to talk about facts. And I only have 14 minutes to do it. And so we start with the ozone hole. Be careful with this. I've heard it over and over again. This is not the global warming CO2 problem. This is a different problem with different solutions. And the good news is that scientists many decades ago figured out what the problem was with the ozone in the stratosphere. That's above the troposphere, okay? I'm still playing with it. There it goes. Anyway, where was I going with this? Oh yeah, so here's the great news. As scientists figured out what the problem is, we know what was destroying ozone in the stratosphere. We know this is a life and death situation. It's not about whether we're going to be a couple of degrees warmer next year or not. It's whether you can walk out in the sun or we can grow food. Literally, all right? And so scientists figured out what the problem was, that CFCs and the chlorine that comes from them was one of the culprits in decreasing the amount of ozone in our stratosphere. Nitrogen oxides was another one. They went to the policymakers. The policymakers saw the scientific data. They acted on that. They figured out what the solutions are, and they are implementing those solutions right now. And it's proof that policymakers and scientists can work together and can solve problems, which leads us to the real discussion today, which is global warming and climate change and all of that. So, well, let's give a round of applause for the policymakers that saw the ozone problem for what it was. That's right. There we go. Is that a little bit too much? I think we got it under control now. Okay, so let's start with the natural reasons for climate change, because I'm supposed to do Climate Change 101 in what is now 12 minutes. So we'll see where this goes. There are natural reasons for climate change. Climates were changing thousands of years, millions of years before we were here, and here are some reasons for them. Some of you may have heard of the Milankovitch cycles. There's 3 basic cycles you should know about. That the Earth's orbit becomes more elliptical and more circular over a period of about 100,000 years. Now this causes climate change on 100,000 year cycles. for instance, right now we're closer to the sun on what date? Does anyone know? We're closest to the sun on January 3rd and farthest from it on July 4th, and it shows you that's not what causes the seasons, all right? So we can get into detail like that some other day, or you can ask me after the program, but we do have an elliptical orbit around the sun, and that's changing on 100,000-year cycles. Number two, the Earth axis is currently tilted at 23.5 degrees. Wow, wait a minute, these slides look like they're coming right out of a book. Could it be a fundamental atmospheric science book? Could it be a book that just introduces you to the fundamental elements of meteorology? Yes, it is. This is nothing controversial. It's nothing that scientists fight over. This is just the facts about our atmosphere. All right, anyway, I'm going to get back to the point. It is supposed to be Climate 101, and I'm trying to portray it as that, all right? Pretty simple stuff. So anyway, getting back to the point, the Earth's axis is tilted at 23.5 degrees now, and that ranges over a period of about 40,000 years, about a degree more and a degree less. When we're more tilted, our seasons are more severe. When we're a degree less tilted, our seasons are less severe. That causes natural climate change. And finally, the big one, the Earth is like a top. Precession it's called, okay? It's wobbling like a top. In a little over 11,000 years, guess when we're going to be celebrating the summer solstice? December 21st. The seasons will have completely reversed by then. Now, it's going to take 11,000 years to get there, so don't, hold your breath on that one. However, the point is this causes natural climate change too. And if anyone were to tell you that, I don't know many reasons for natural climate change, there are plenty of them. Here, I'll show you a few more. It's not just the Milankovitch cycles. Over millions of years, we've had plate tectonics. That's changed ocean currents. It's changed the location of continents and oceans. That changes climates. We have sunspots. That's a huge 22-year cycle. 11 years after we have sunspot maximums, which cause the sun to emit about 0.10% more solar radiation. 11 years after that, we get a sunspot minimum. That causes climate change. There are natural reasons for climate change. Volcanic eruptions. Isn't that a fantastic photograph? Wow. It feels like the eruption of this organization, the California Climate Change folks, It started as a small group, and it's erupted into this enormous movement. It's quite impressive. Anyway, what happens? Those big volcanoes, it was El Chichon in the early 80s, in Mexico that blew up, that changed climate. It threw enough aerosols in the upper atmosphere that we cooled off by more than a degree for more than a year. Then we had Mount Pinatubo, the biggest eruption in the 1900s, and that, again, threw enough aerosols in the upper atmosphere and reflected enough solar radiation that it cooled off Earth's atmosphere by about a degree for more than a year. So there are a lot of these reasons for natural climate change, and we should know them, because those are worked into the formulas. Those are worked into the models that climatologists use when they're trying to figure out what's going to happen next and what happened in the past. For instance, about 18,000 years ago, when we had our glacial maximum, our last glacial advance during the Ice Age was at its maximum, look at where the ice was. Boy, that was a different climate. Here in Santa Monica, it felt more like Seattle during that time. Right? And that was just 18,000 years ago. I know, I have some colleagues that are that old. Right? Well, anyway, you begin to understand climate change a little bit better if you know about those natural reasons for climate change. Now let's get into what's going on in our atmosphere over the last century or so. Most of you know that the sun, being a hot body, emits more in the shortwave part of the electromagnetic spectrum, right? Hot bodies give off shorter wave radiation. That shorter radiation comes from the sun into our atmosphere. It heats up the Earth's surface and the oceans. And because, hopefully, last time I checked, we weren't at 6,000 degrees Celsius yet. So because we're a much cooler body than the sun, we emit in the long wave, the infrared part of the spectrum. And that's where it gets interesting. All right? So it looks sort of like this. Shortwave energy comes in from the sun. Our atmosphere is mainly transparent to it, mainly, as you will see. That heats the Earth's surface. The Earth's surface warms and then radiates long-wave energy out. And it is those greenhouse gases that are responsible for absorbing that long-wave radiation that they allowed the shortwave in, but they're selectively absorbing the long-wave radiation, all right? Anyway, it's called the greenhouse effect, and if it wasn't for greenhouse gases, Earth's atmosphere would be about 30 degrees colder Celsius than it is now. Just about 60 degrees Fahrenheit. Boy, if you think low clouds and fog are cool, check that out. So, thank you. Let's hear it for greenhouse gases, giving them a round of applause, right? Because without them, life on Earth as we know it would be impossible. And as soon as the sun set each night, we cool off like 30 degrees just at the snap of your fingers, all right? So what are these greenhouse gases? Carbon dioxide, water vapor, a very important greenhouse gas, methane, nitrogen oxides. There are others, but you can see this is what we call the radiation budget. As radiation from the sun comes in, you can see about 30% of it is reflected back out into space and doesn't affect us. But about 19% is absorbed in the atmosphere and the clouds. And what's the big arrow? That's the radiation that makes it to the Earth and ocean surface. And that is the radiation that's ultimately responsible in mainly heating our atmosphere. Uh-oh, now it won't. Oh, by the way, did you know that there is just kind of a side box here. There at the equator is an energy surplus. There's more energy coming in than going out. And at the poles, there's an energy deficit. There's more energy going out than coming in. The net result is you think that the equator should constantly be getting hotter and that the poles should constantly be getting colder, right? But they're not. Anyone know why? Okay, I'll tell you. It's winds that circulate excess heat and cold. That's about a third of it. Ocean currents do the same. They also circulate excess heat and cold. And then latent heat, as water is changing state in the atmosphere, it circulates that excess heat and cold. So thank you for those circulating currents. Well, look, if we now know what the mechanisms are that heat our atmosphere, remember, it's not the shortwave energy from the sun that heats the atmosphere. It's the energy from the sun that then heats the surface. And then the Earth's surface that gives off, what kind of radiation was that? Long-wave radiation. So that the Earth's atmosphere is almost primarily heated from the bottom up by long-wave radiation. There's no argument about that. That's been taught in basic atmospheric science classes for many, many decades, long before we had this discussion about global warming. This is called the greenhouse effect. This is what makes our atmosphere livable, all right? So that's the point I wanted to make. If I missed everything else in this presentation, if someone were to ask you, what is the basic science of how our atmosphere is heated, you can tell them, well, it's heated mainly from the bottom up by long-wave radiation that is absorbed by greenhouse gases. The net result is, you have to admit it, change the chemistry of the atmosphere, you're going to change the weather. There's no argument about that in the scientific community. Did I say no? I meant it in the scientific community. And this is the curve. You've seen it many times. We're not going to get into detail because I'm going to run out of time. We've been measuring the amount of CO2 in the atmosphere since the 1950s. We know how much CO2 was in the atmosphere before then, and I'll tell you about that in a second. But does anyone see a trend, by the way? You know, these are seasonal variations, by the way. Some of you probably know that since the northern hemisphere has so much land mass, currently when our trees and the colder climates are dropping their leaves and they're not carrying out photosynthesis and the photoperiod is shorter, they're not pulling in the CO2, so the CO2 content comes up a little bit seasonally. Then it'll drop again in the spring and summer. But again, you know, there's an obvious trend here, and we know what's causing this. Scientists know that about 80% of this curve is a result of burning fossil fuels that have been under the ground for millions of years and are now being burned in the last century. Another percentage, perhaps 20% or more, is due to the destruction of rainforests where we have this huge carbon dioxide sunk, right? So this gives you an idea of the measure of carbon dioxide in our atmosphere. You've seen a lot of these. It's just like flipping through a book, isn't it? There's nothing really complicated about this stuff, all right? We see that the amount of carbon dioxide has fluctuated. This goes back 1,000 years. And of course, it's way up here now, higher than we've ever recorded it and higher than we know that it's ever been. Hey, let's give it a round of applause because we made it to 400 parts per million. Thank you, carbon dioxide. Way to go. Yeah. We were always looking forward to that one, weren't we? All right. There are other gases, methane, nitrogen oxides, etc. So, you know, it stands to reason if any rationally thinking person would look at the carbon dioxide content, knowing that that was one of the major drivers of our greenhouse effect, seeing that it's increased by so much just over the last 1,000 years, you would expect this curve to make sense, wouldn't you? All right? If it went in any other direction, it'd be really a big surprise. And so you see the mean up here, that's the black line, and why is it there? Well, that's because our temperatures have gone up about 1 degree Celsius in the last, 100 years or so, a little bit more Fahrenheit. And the net result is it's brought that mean temperature for the last 1,000 years up quite a bit, you see. The mean should be drawn right here. This is natural climate variability. You can see it here, all right? By the way, how do we know what was going on 1,000 years ago? Ice cores, right? And when it snows, it traps air bubbles inside those snowfalls. And we can go back hundreds of thousands of years and figure out not only what the gases in the atmosphere were, but what the temperature was. This goes back to the 1800s. You see another temperature curve that has an obvious trend. By the way, does the temperature go up every year? No, it doesn't. It drops for a year or two, then it starts on again, doesn't it? Right? So this isn't something where we go outside and we notice that every year is warmer than the one before. It's a trend that's been going on for a century or so. Now, finally, we get to this curve, and we see 3 different curves here. Carbon dioxide, methane, and air temperature. Does anyone see any correlation between carbon monoxide, methane, and air temperature over the last 400,000 years? You can't find the curves, can you? Because they're the same, all right? Talk about correlated. Every time we've had an increase in CO2, we've had an increase in temperatures, all right? Every time. There's no exception to that. And now this goes back to over 10 years ago, we knew this. Over 10 years ago. Now we've brought this curve out to over 800,000 years. And we can tell you that there's more carbon dioxide in the atmosphere now, by far, than there have been for more than 800,000 years on this planet. In fact, if you look here, this is 325 parts per million. Where are we right now? We're off this chart. It's the first time that's happened in just about 1 million years, and we know that now. That's not being argued in the scientific community. We can talk about how the ice is melting, but I don't have time for that. So here's what we come down to. We come down to models. And what some scientists have been doing, well, all of the big climate scientists have been doing, is they'll run their models backwards where they know how much CO2 was in the atmosphere and they know what the temperature was then, right? And they'll try to trick the computer to see if the computer can predict what the temperature would have been then. And then, if it does, then they know that that model works best to try to predict what? The future. Because this is not controversial. We know what happened in the past. You saw that data, all right? No one's arguing about that. And so here's where the models come out. And remember, by the way, my handout, are we going to be able to get that out to everybody? Okay, I have a handout that updates you on the latest statistics. I'm almost done, by the way. I'm a little bit over, so don't worry if you're getting nervous. I'm getting there, right? Yeah, look, this goes back many years now. We knew that the models were showing this trend to be the future of Earth many years ago. Okay, this isn't something new for us. But what the new study that has come out by all the major climate scientists that are keeping up with this in the world, the latest IPCC results, are showing that this possibility of temperature changes is narrowing a little bit, right? So we're getting a little bit more specific, a little bit more knowledgeable about what we can expect in the future. And it ranges from roughly about a little over 1 degree Celsius increase in temperature, about 1.5 degrees. That's about 3 degrees Fahrenheit by the year 2100. Worst case scenario could be up around 4 degrees Celsius, which is about 8 degrees warmer. And so it's more complicated than that, as you all know. I'm supposed to do Climate 101 here. It's an impossible task in the time I have. But here's the problem. Some people will say, well, there's a lot of uncertainty here, right? And I'll say, well, this is the curve that shows if we stop burning CO2, or if we stop burning fossil fuels right now, we stop putting CO2 in the atmosphere right now, what's going to happen to temperature? Not even that one goes down. Does anyone know why, by the way? Yeah. It's going to be here for a while, that's right. So even with that, we get a little bit of warming. Of course, that's not going to happen. So when we look at these different models, they show a different amount of warming depending on if we get negative and positive feedback mechanisms that I can't talk about because I'm already over time, all right? So this new curve, by the way, looks almost like this. This is the latest that just came out. And it's just a little bit more narrow. There's a little bit less uncertainty. You know, people say, well, if there's uncertainty, then why should we act? Well, what if the uncertainty ends up here? You see? So that uncertainty question can go in either direction. And if it ends up here, of course, that's catastrophic climate change that will completely destroy ecosystems on Earth as we know them. And billions of people will die from that. There's no question about that. You can go online and get the latest IPCC report. They show you who's been warmer, who's been cooler. They show you what we expect in the future. And I want to end with this one. See, I said end. I hope that'll make our timer happy. I want to end with this one map that shows why everyone isn't going to get warmer. But what we do expect is that as climates change, and we've trapped more heat in the atmosphere, what we do know is those convection cells. Remember I talked about that, the wind that mixes excess heat and cold. Those convection cells are on steroids now. And nature is trying to figure out how to redistribute the excess heat that is being trapped by those additional greenhouse gases. And so one of these scenarios suggests that as Greenland ice sheet, and you read that, yes, it has been melting. I have the latest statistics there for you. As the Greenland ice sheet melts, that fresh water flowing over the ocean, being lighter, less dense than salt water, has the potential for blocking the Gulf Stream. If that were to happen, while most of the rest of the world were warming up, this part of the world would get much, much colder, the northwest part of Europe. And so it's these very detailed problems that scientists are trying to work out that you're going to hear about after I'm finally done. Geez, you're thinking, is he ever going to finish? It's these very detailed problems that we have the most trouble trying to figure out what really is going to happen here. So here's what we can tell you. We know we're getting warmer. We know we're going to get warmer. But that doesn't mean everybody's going to get warmer. What is happening everywhere on Earth is an increase in the climate anomalies or the weather anomalies, where you hear it everywhere you go and the statistics show it. The hottest ever, the coldest ever, the longest dry spell, the worst flooding. These are not coincidental. Some of them are, but put them all together and they add up to the climate change that you've seen on these charts. And so this is what scientists aren't arguing about. The uncertainty based on the details I just mentioned to you are what climate scientists are arguing about. Okay? So I hope this was impossible for me to do. You know, in front of an audience like this, the people that I respect so much, and I'm way over time now, and see, I told you should have brought the hook.